Hello everyone, I am Maxim Islam from NC State University. I am finishing my PhD this December and looking for opportunities. Today I am going to discuss about brown carbon in biofuel combustion emissions. So the main research question is, does brown carbon from real-world biofuel combustion emission matter? We found that brown carbon in biofuel combustion can be a major player along with black carbon to govern radiative forcing. Let's talk about the sources first. So we analyzed samples from a range of devices, including 3 stove types and charcoal kilns. The stove emissions were measured in a field campaign in India, whereas charcoal kiln emissions were measured in Malawi. I should mention that the sample selection was not completely random. We chose them in purpose to span range of EC2 ratio and MCE. In my next slide, I will show the distribution of these parameters for different stove types and devices. So this figure shows the EC2 ratio of samples for 4 biofuel sources. So we don't see a significant differences in EC2 ratio between stove types. However, EC2 ratio of charcoal kilns are lower than the stoves. The trend is kind of similar for MCE. Now talk about measurement. So this figure shows a typical measurement day in real-world kitchen, where stove emissions were measured using STEMs, that is stove emission measurement systems. For this project, we used the collected filter and applied methanol extraction approach to extract organic carbon, and finally applied spectrophotometry to get the brown carbon extracted, methanol extracted brown carbon MAC spectra. So for today's talk, I will discuss 3 specific research questions. The first one is, what are the light absorption properties of OC from diverse real-world uses of biofuels? This figure shows the brown carbon MAC at 365 nanometer for 4 biofuel sources. We don't see a significant difference between traditional and improved stoves. However, the MAC of chimney stoves are lower than non-chimney stoves. MAC of charcoal kilns are similar in magnitude to chimney but lower than non-chimney stoves. This figure shows the AAE distributions, and we see that AAE of chimney stoves are significantly higher than non-chimney stoves, and this is true for charcoal kilns also. Here we'll discuss the imaginary refractive index of brown carbon, that is K brown carbon, and wavelength dependence W of our samples in context of a recent review. This figure was taken from a recent review study where Saleh showed that brown carbon can be represented by the characteristics K550W pair, because for all brown carbon types or sources, K550 and W are inversely correlated. This inverse relationship indicates that less wavelength dependent brown carbon will have high light absorptivity. Now I will put my values on this graph for comparison, and this is it. So you can see that our values lie between the smoldering biomass burning and high temperature biomass combustion zone. On this figure, these points represent lab cookie stove testings. Interestingly, OC emission factor in field are typically much higher than in the lab, however, appear to be less absorbing, which is really interesting. Now I am moving to my second question, which is, can we predict these properties based on more easily available factors like combustion conditions and sample properties? So this figure shows the brown carbon MAC at 365 nanometer against EC2O ratio. And you can see a moderately strong positive correlation between them. However, the correlation between MAC and MCE is weaker than this. It indicates that EC2 ratio is a better proxy of burn conditions than MCE to show its link with brown carbon properties. In my next slide, I will show the values from a lab cookie stove studies for comparison. So here, the black cross markers indicate the lab values. There are some differences between their values and ours. So their values showed stronger correlation. compared to ours. Also, their slopes were steeper than ours. However, our values show a wider range of EC2A ratio and MCE values from real-world biofuel combustions. I should mention that AAE does not show any trend with combustion conditions. So now I will discuss how brown carbon properties are associated with volatility. For that, I used OCC analyzer OCPIX values. So this table shows the protocol used in the analyzer, and if you go down, it indicates the decrease in volatility. So this figure shows the MAC values against OC3 fractions, and you can see a moderately strong positive correlation. This is true for OC4 fractions as well. However, the opposite is true for OC1 fractions. These findings indicate that less volatile OC fractions will have higher light absorptivity. So now I'm moving to my last questions, which is what is relative absorption and relative impact of black carbon and co-emitted organics from these sources? For this relative comparison, I used me modeling approach, where K of brown carbon were calculated from methanol extracted sample properties. Other inputs like KBC and real effective indexes were taken from literature. For the size distribution, we used lab test for similar stope types. So using this approach, I calculated brown carbon contribution to total absorption, and it is shown here. So you can see that the percent of brown carbon absorption varies across samples. In this figure, the x-axis represents the percent of external mixing, and we can see that as the percent of external mixing go down, the percent of brown carbon contribution also go down. Next, the relative radiative forcing impact. For that, I calculated simple forcing efficiency of PC and brown carbon using this formula. After that, I calculated direct radiative forcing ratio, that is DRF of PM to DRF of PC using the simple forcing efficiency values. And this figure shows that DRF ratios. Here, the horizontal red lines indicate the transition from cooling to warming. The blue lines indicate BC core with absorptive OA code, while the black circles indicate BC core with clear coating. And the difference between these 2 points indicate the contribution of brown carbon absorption to DRF ratio. We can see that with an increase in EC2 ratio, brown carbon absorption contribution decreases. Also, with an increase to EC by OA, the DRF ratio goes from cooling to warming zone. For the BC core with clear code, this transition happens at an EC by OA of 0.2. However, due to brown carbon contribution, this transition happens at an earlier stage, showing the contribution of brown carbon in radiative forcing. Now I will show these values from a lab biomass burning studies for comparison. And this is it, where the blue lines and black lines indicate the same as blue circles and black circles for our case. So in general, we see the trend of ours similar to them. However, there are some differences. The transition from cooling to warming due to brown carbon contribution happened at an earlier or lower EC by OA ratio than ours. Also, they mentioned 0.05 to 0.1 EC by OA as the atmospherically relevant range. However, our values show that EC by OA of real-world biofuel combustion can go beyond that range. So let's talk about the conclusions. Cookstoves and other biofuel use emits brown carbon with properties linked to BC to OA ratio and volatility. Fuel emissions are more dominated by smoldering emissions than lab testing. Contribution of brown carbon varies across samples and mixing assumptions. And finally, brown carbon in biofuel burning emissions can be a major player along with BC to govern climate forcing. That's all. Thank you.